Hello, everyone. Welcome. Today we have Dr. Wei Yang from SLAC, and he will talk about Xrootd and Xcache. This talk will be recorded and be available later. Wei is an experimental high-energy physicist working on Atlas computing, and he is at SLAC since the year 2000. He has built and is leading Atlas experiments less than tier 2 facility since 2006. And along with Andy Hanushevsky at SLAC, he brought Xroot storage system to Atlas and Xroot computing. And he has worked on various Xroot projects such as Xcache, Federated Atlas Xroot, third-party copy with Xroot, etc. He is also an active member in open science community, open science Xroot community, and has helped various Xroot related projects in the science communities beyond Atlas experiments. Okay, Wei? Go.
Thank you, Alex. So I will be talking about mostly Xcache, but since Xcache comes from Xroot, I will also explain the Xroot a little bit. I don't know whether Andy is on the line, but he's the main developer, and I hope he's there to help us answer any questions.
I am here.
Oh, great! Because once I open this, I can see, and the screen the pictures keep on overlapping my slides. So I will firstly quickly go through Xroot and its plugin architecture, how we scale up, and one of the important things is monitoring, because if you are deploying a large scale of anything related to Xroot, you probably want to know what's going on and what's happening internally. So in addition to that, then the main focus will be the Xcache. I'll be talking about the features of Xcache and how we expand the functionalities of Xcache. I will give 2 examples on that, and that will bring up some kind of interesting thoughts and discussions. And then in the end, I will bring up one of the keys, since will be interested, is the security and the general purpose shared cache, the idea, and what works, what may not work. So start with the Xrootd. So Xrootd was a open storage. It's a storage system. It's open source storage system. It was developed during the Baba time. I believe that 25 years ago. It was mainly used to serve the static science data storage like HTTP data, and it was lightweight and reliable. And all these bugs and things was sort of figured out and fixed during the Baba experiment. The current form of Xroot software stack allows plugins at almost everywhere. So these allowed us to greatly expand Xroot's functionalities. And it also is because of this reason, the plugin architecture and the open source allowed us to attract many contributions from people outside of the core Xroot team, which is actually pretty small. So the protocol is supported by many storage systems like Dcache, EOS, DPM, and Rel Echo Ceph. So I'm not sure everybody familiar with these storage systems. These are mainly used by the high energy physics community, especially the LHC community, as their storage systems. So while it is great to attract many contributions from people outside of the core team, these architecture obviously bring us some challenges. I believe that Andy has to spend a large amount of time to keep track of all these contributions and to make sure that they can peacefully exist with each other. And also each contribution comes with its own long list of configurations and parameters. And so this has to be documented, and sometimes it's easy to confuse and miss something. So I'm going to talk a little bit about the architecture and show where is Xcache and how we expand that thing. So the first part of this is the core component of Xroot as a storage system. So you have a core and management system in the center, which do the scheduling, the threads, and the memory management, and manage the connections, etc. So these core components views the storage as a file system, but it's a generic file system. So there is an open file system layer, which the core system talk about to the storage. And below that is a storage plugin, which allows you to do all sorts of plugin, all sorts of storage systems. One of these is obviously the POSIX file system, of course. That's what the Xroot starts. So on the left, you have the protocol which will deal with the client. So the data flow between the service and the client, so that using this Xroot protocol, which comes along, comes with its own many security plugins like Kerberos, GSI, SSS, and in the future we will have JSON web token. So to expand this, to expand the protocol support, we first add a protocol bridge, which allows other protocols to map to the Xroot protocol and then use these other protocols to talk to the client. So obviously with that bridge, we have an HTTP plugin, and along with its own security plugins like GSI or JSON Web Token. So with both protocol, a client can talk to the storage system. At this point, it's still just the storage system with either root protocol or HTTP protocol or their TLS versions of the same protocol. So to expand support for other storage systems, we had some plugins to add to the open OSS layer, allowed us to talk to SAF, allowed us to talk to HDFS, along with the POSIX file systems. So if you look at all these plugins to OSS, they are essentially plugging to a local or near storage systems. So what about data at a remote location? So with that, we add another plugin called proxy plugin, which has an Xrootd client component inside. With this plugin, we can actually talk to a remote data source with root protocol, so that with this plugin, you can see that the data flow from the rightmost remote data source all the way to the leftmost client through the Xrootd. Mostly we use this to route traffic or things like that when we are behind, or when users for some reason wants to access to the remote storage but cannot. Now, once we have these, we start to think, can we actually cache the data flowing from the remote location to the users? So there's another plugin added to this proxy plugin called Xcache, or we call it disk cache plugin. So while the data flow from right to the left, we also save that data piece in the local storage. This allowed us to cache and enhance the performance. Now, with the proxy plugin that has Xroot client inside, and Xroot client is also a plugin architecture, we actually can support another protocol. We just developed another protocol like HTTP plugin to the client, and then we can speak HTTP protocol or HTTPS, of course, to the remote storage. So these allowed us to have a Xcache that speak both protocols to the client and to the remote storage, and you can mix this in any combination. And one of the last thing I want to mention is another plugin to this OSS layer, which is called name-to-name or end-to-end. This is the place where we can enhance the functionality of Xcache. So I will give two examples. One is how we integrated Lucille to Xcache to enhance its functionality. The other is Xcache H, which deals with the HTTP protocol. So I want to say that this is a vastly simplified picture of Xrootd and Xcache. There are many things that are not shown here. I put it here in order to help me to explain the slides. It is by no means say that this is a complete picture. If you want that complete picture, you can talk to Andy. Maybe he will draw you a 4-dimensional plot. So scaling up. In the previous slides, I didn't show how we are going to scale up on this. Obviously, we need to do that because one single machine always has its limitations. So the way we scale up is to add a CMS daemon pair with the Xroot daemon. The Xroot doesn't talk to each other across the nodes, but CMS does. CMSD does not deliver data, but it's just a clustering function talking to each other and figure out who has what. So with CMSD, we can form a cluster of nodes. So here is the traditional Xroot storage on a single node. Instead of just the Xroot daemon, we have a CMS daemon. We can add another one, and we can actually add 64 of them. And on top of them, we add another Xroot and cmsd without storage. We use that as a redirector so that a client can talk to this redirector, and then the client will be sent to the data server who has the data. Excuse me. So in this architecture, there is no data striping across the data server, or file either reside in one data server or the other, or you can have two copies. That's fine. It's not. There is no striping, and there is no locking as well. So the redirection mechanism sends the client to where the data is, so that the data does not flow through the redirected data, go directly from data server to the client. So this architecture, without striping, there is no locking, dramatically simplified the metadata operation. We don't have to actually keep much of the metadata at anywhere at all. So this makes this architecture and all these services relatively simple. Now, this is good for analyzing static science data. It is not something like analyzing data that keep on changing, but for static science data, this is probably a good way of storing the data. So this is a traditional view that each node has its own storage, but there are other cases, like this case, where you have a large shared storage pool, like in the HPC, you have a very large storage system, 27 petabyte, and you can serve it from one Xroot server, which probably will limit you because one Xroot server only has that many CPU and network bandwidth. But you can have multiple Xroot servers to help you deliver the data. All of these Xroot servers see the same storage, and you can put a cmsd on top of it. It will work as well. Another way to do this is this orange cluster, which you have Xroot and cmsd. Instead of talking to the local storage, they talk to the remote data source. And this is something we call a proxy cluster, and it's what Xcache actually is. So you have this gray cluster, the blue cluster, and orange cluster. We can actually put another redirector on top of them to glue all of them together if you want. Usually we don't necessarily do that, but this is we can do it if there is a reason. So the client can start with the top level redirector, and ultimately the client will be sent to where the data is. This is how we scale up. The client can actually start with any of these lower level redirectors or data centers. So the redirection mechanism we are talking about is really based on a real-time query of a single question. Who has this file? And then the client will be sent to that location. The information obviously will be cached. Now, this is a real-time query. There could be other ways to redirect this. For example, you can use a database, or you can use a hash function. We chose to use the real-time query. There are other storage systems use database, for example, DTM. We chose to use the real-time queries, and so far we have built a lot of experience on how to handle it and handle it correctly. So monitor, when you are building a large Xroot or Xcache and things like that, you want to see internally what's going on. So you do want to go into monitoring. Xroot doesn't provide the monitoring dashboards and analytics, since there are plenty of industry tools to do that. But what Xroot does provide is to send out UDP packets on summary or performance information or event data. So since we're talking about cache, I will just give you a few examples of what the summary data could be. For example, how many bytes go into the cache during that last period, like 5 seconds or 1 minute or 5 minutes. How many bytes out of the Xcache by request, the cache keys and cache miss, and the number of bytes. What did I write? Completely overlap. The number of bytes go into the cache, but oops, it go into the cache, but did not have a chance to save the data because probably the storage was too busy. That's also summary information. The detailed event-based information has many streams. We organize them in streams. I picked up a few examples. The U stream tells you the client's login and the client's identity information. The D streams tells you who opened what file. And the T streams tells you which part of the file was read at what time. For example, these reads start from this offset and have this many bytes read. So this kind of information, so monitoring will give you all these details, and then you can send it to your wonderful analytic platform and display them. So there are several other interesting things about Xroot, which I'm not going to go into detail, but there are two things I want to mention. One is the POSIX library. Xroot, in addition to its own I/O functions, it also supports POSIX I/O functions. There is even a POSIX preload library, so that if you write your own I/Os in POSIX I/O functions, you can actually use the preload library so that it will work with the Xroot storage or Xroot protocol. The other thing relevant to this here is the FRM, File Residence Manager, FRM. It is essentially originated from a tape staging systems. During the data staging, you can run a customer script. And in that script, you can do anything you want. So this essentially allows it to function as a whole file cache. So the differences between this one and Xcache is that Xcache will prioritize the data block you want from that file and try to get that block first and deliver it to you. This one doesn't care about that. This one just put the client on hold and fetch the whole file and then start to serve the client. There are pros and cons for both, but this one is also something that has seen lots of use. So with all these, I'm going to dive into Xcache. So for most people, Xcache is the whole Xroot software stack that deal with save data on disk as a cache. So internally, Xcache refers to a plugin, that specific plugin that was developed by UC San Diego with SLAC helping them do that. It is, think of it as a Xroot-like cache. We actually learned a lot after we developed this. When we try to add functions, we actually learned a lot from Xroot, and I even find this very old Xroot FAQs, which is very old, but it actually tells you a lot of things why Xroot do things in certain ways and not other ways, and how they address various kinds of problems. But here, I want to sort of emphasize the difference between Xcache and Xroot. Obviously, Xcache will support, they both support HTTP and HTTPS protocols, but Xcache supports root protocol, which Xroot supports and many other protocols. Now, Xcache is multi-threaded, Xroot is single-threaded, so that will allow Xcache to use all your CPUs. Xcache also supports async data fetching in the root protocol. I believe that HTTP protocol with HTTP pipelining also allows you to do some of that, although not perfect, but you can do some of that. One key difference is that Xroot a cache file as a whole file, while Xcache can work at 5-block level. So you can say that the first block of the file, second block of the file, like that. So with this, because of these differences, Xroot prefers smaller files so that it can fetch it quickly. And probably also because of the single thread, Xroot prefers smaller file, but Xcache doesn't really care about the size of the file. It can be small, it can be large. Now, we're dealing with file blocks and we're dealing with partial file caching. So obviously Xcache prefer static data. If the data keep on changing, then it's hard to keep track, and especially keep track of data blocks. The scaling up mechanisms is also quite different. Xcache scales with the cmsds, those kind of clustering mechanisms. Squid cache, I believe, sort of use the sibling query protocols like ICP to understand who has what. Xcache also allowed us to customize the cache behavior because of the plugin architecture. So a few details about Xcache. So before we go that, I want to keep reminding people that Xcache is both a server from the client's point of view, is a server, but Xcache itself is a client. It's a client to fetch data from the remote data source. So for each file that was cached in the storage, there is a state information file maintained in parallel. This state info file has the information about original file size and how many blocks and which blocks is a bitmap that are committed to the local storage and how many opens and reads and writes, etc. informations. I'm not sure that I will go through all these details, but I want to say that back to 2 years ago, there was some discussions of whether we should make Xcache writable, although it's quite challenging, but it's possible. But it turns out that most people are only interested in read-only cache, so we didn't really go that route to work on the writable cache. So another optimization was Xcache on HPCs. This was driven by an LDRD project at LBNL, and we actually run Xcache on the NERSC DTN since that. So if you look at on the left plot, from the cache point of view, here is the architecture of the HPC. So you have HPC batch nodes. You have the last file system with a huge last file system, and you have DTNs. All of them are glued together by the InfiniBand-like fast link, which speaks RDMA. So when the jobs running on the batch nodes needs the file, Xcache can certainly get the data from the remote data source, and then use as the data blocks coming in, Xcache start to deliver data to the HPC node. Now, with this, we know currently we can only deliver data through TCP connections through Ethernet. We cannot deliver it through the InfiniBand. But once the file is fully cached, the Xcache will tell the client, tell the jobs on HPC nodes, says that, okay, this file is fully cached, and here is its file location on last file system. Why not you reopen it and read from there? This will be nice because from now on, the HPC nodes talk directly to last, which will utilize this RDMA network, InfiniBand network. So this all happens between Xcache and the low-level Xroot client library on HPC nodes. It doesn't, the high-level applications doesn't see all these changes. So it's completely transparent to the application. So this is currently is a way for us to utilize the fast internet, fast link in HPC environment. So what we still want is to be able to run Xroot protocol over RDMA, which is we haven't implemented that yet. So we sort of partially implemented how to utilize the RDMA. So the protocols that Xcache support, there are two main protocols right now, Xroot and Xcache support. One is obviously root protocol. The other is the HTTP protocol plus their TLS siblings. Xroot protocol is a sort of a standard in HTTP community. It's actually not specific to HTTP data. It's a generic remote data access protocol, and it also supports POSIX and POSIX preload library. It is stateful and it's a binary protocol, so expanding that protocol requires some work. So one of the key features is that it supports async network I/O. On the other hand, HTTP protocol or HTTPS is an industry standard. It's stateless, so it's text headers is very flexible, allows you to add functionalities to it. Obviously, that comes with a price. The price is the overhead of the header. Because it's a stateless protocol, when you're using HTTPS, which is a TLS, you want to avoid sort of re-authentication every time, or re-establishing this encryption channel every time. So HTTPS implements some kind of things called credential caching. So to avoid that, this is effectively turned HTTPS into a SAML stateful protocol. Now, in terms of async network I/O, HTTP's solution is to use pipeline. It's not quite successful, but it still can do something about it, although sometimes you still see blocking happens. Xroot protocols is natively supported on the Xroot server side, and because of this protocol bridge, we also add HTTP protocol support package to do that. It's called XRD HTTP. On the client side, the Xroot client library also has a plugin architecture, which allows us to load plugins based on the protocol user use. The default is Xroot protocol, but there is also a plugin called XRD CL HTTP, which was developed based on the Davix library, which Davix library is developed by CERN, which has several layers of interface. One, the bottom layer is the direct HTTP interactions. There, on top of that, there are also treating HTTP like a POSIX file systems, which is handy for us to use. So that's why we chose Davix library when we implement this plugin. So to access Xcache. So if Xcache is configured to only fetch data from a fixed location with either root or HTTP protocol, then you configure that, then in the URL, you only need to specify Xcache hostname, and you give the protocol, you give the hostname, Xcache hostname, port number, and then the file path, then you will be able to access it. Now, there is another way to do this. Xcache can be configured to fetch data from any data source instead of the fixed data source. So the way you do that, the most popular way in the RFAS community we do that is to use a concatenated URL. So you have root protocol talking to Xcache, and then you concatenate the final destination. For example, root at cern.ch eos file. Behind that Xcache URL, so that when Xcache sees this, Xcache knows, okay, you actually want to talk to this particular data source, and it will fetch the data from them. So there are many combinations of this because of the root protocol and HTTP protocol, and also because of the TLS variations. So we even, it's not quite popular, but we even try to emulate the behavior of Xroot. Xroot has this HTTP proxy environment variable. We try to emulate that with HTTP root proxy environment variable to do similar things. But note that I didn't say anything about HTTPS protocol, because this is kind of things that I will discuss later. There is a lot of interesting thoughts on that. Now, when the client accesses the remote data, sometimes it needs a credential to do that, to authenticate. In this case, the user's credential will not be forwarded to the remote data source. We have to rely on a shared credential because it is not practical for us to keep track of which file or file block was owned by which data. If this block of the file is fetched by this user, can the other user use that data block? Something like that. It's not practical to keep track of it. So we use shared credential, which means that it's sort of good for a community with a common access privileges to use the same cache, to share the same cache. So expanding the functionality of Xcache. So I think so far I have seen that most of the there are several plugins exist to expand the functionality of a simple Xcache. All of them IC explores the something called the name-to-name translation. The end-to-end is actually a C++ class in Xrootd. So this name-to-name has two key functions that are called for every time a cache request coming in. One is the LFN, logical file name, to PFN, to the physical file name, which essentially converts an incoming URL to an outgoing URL. So you can manipulate when the user says, "I want this," you can actually manipulate where you get the data from. The other is called PFN to LFN, which means that it's meant to say that when you are going to get this data from this data source, what is actual storage path that we are going to use to save these files? For example, if a file has multiple copies, you can get from either one. If the file exists in multiple locations, you can get it from either locations. But with this function, you know that all these files are the same files in cache. They can share the same cache entry. So you can do a lot of things in these two functions. So I am currently aware of 3 plugins exist. The first one is just a storage plugin, which I'm not going to go into. The second one is a Xroot plugin, Xroot end-to-end plugin, which utilizes central data management database to choose the best data source and also to provide failover. So this is an example that I want to show how we use a central data management system when it exists. The other one is Xcache H. It is mainly used for HTTP protocols, and one of the key functions like script is to be able to detect the change at the data source. And then based on that, you will determine whether you want to flush the cache entry and refetch or not. So this is an example I want to show how show the limitation of caching when you have end-to-end encryption request. So what will happen with a cache if people want end-to-end encryption, or people don't want end-to-end encryption? So the first Xcache with Xroot end-to-end. So I'm not sure everybody familiar with know what is Xroot. Xroot is a data management system for Atlas. Atlas adopts this, and the whole LHC community adopt this grid computing model, which basically spread the data in Atlas case, spread the data to 130 plus sites. And so there is no single site that has a full copy of everything. So the data are distributed around the world, and Atlas Xroot organized the same kind of data in data sets so that each data set has many data files. So when users analyze them, they said, I will pick up this data set and analyze everything in these data sets, every file in these data sets. So Xroot will keep track of each of these files, and each of the files has a logical name in Xroot, along with the file size, the checksum, expiration dates, and probably ownership. And because we distribute data around the world, we need to record which site has this file, how many replicas we have around the world, and where are they. And these locations can change over time because when we move data around. Another key feature for Xroot is that once a file is created, the data file will never change. If you generate a new version of this file because your software improved, you create a new file. It is a new file. So from user's perspective, if you want to analyze a data set, you first will have to figure out what is in the data set, which files are in the data set, and then you'll find out where's the location, and then you download them, or you do a direct remote. And if you do a direct remote access, you will have to keep track of the file location change. Sometimes data can disappear from one site and show on another site. But with this plugin, the user does not have to deal with this. They only need to know the logical name in the data sets, and then they will access the Xcache using this logical name. Inside the LFN to PFN, we do all these magics with Xroot to figure out where the data source has been changed, and if there is a first data source fail, we try the second data source, and all these kind of complicated things. It's probably quite easy to say all this magic, but actually it's quite difficult to. It's probably easy for humans, especially like me, which has experience, to understand there is a side problem, but it's probably difficult for for the client to figure out the failure modes on the data source and fix all the deal with all these problems. So one challenge Alex actually asked us is that, well, this is with a central data management system. What if there is no such data management system? And what do we do, especially since if we are going to have several Xcache siblings not sitting next to each other, but sitting around geographically separated locations? What do we do? Can we sort of discover each other's contents? This is a good challenge, and we are thinking of it about sort of going to Xrootd and see how Xrootd deal with this situation and what kind of protocols they use to deal with that. This is the first location, first example of where there is a central data management system. The second one is Xcache H, which is mainly focused on the HTTP protocols. So all this happens in the PFN to LFN. We actually don't use the LFN to PFN. The LFN to PFN is basically pass the incoming URL to the outgoing URL without making any modifications. So in this PFN to LFN, we do a lot of things, magics we are inside. So one thing is that we map the storage, the full URL to the storage. So the full URL includes the client protocol the client used, the hostname, the remote data hostname, port number, file path, and CGI information. We save that. Well, we use that to map the storage. So each URL, even if it is the same URL, but if it is the CGI is different, it's a different cache entry. So another thing is that you fetch the data, but after an initial period, then Xcache will say, okay, maybe after this period, the data could change. So Xcache H will start to check the modification time at the data orange to detect any change. This will make decision on whether the cache should be purged or not. Well, with these, you know that there is always a risk of during this initial period, what happens if the data source changes, and then you have a sort of old data or other obsolete data. So this risk always exists. It also exists in the Xrootd as well. But the mitigation is that if we deal with static science data, we most likely will be able to avoid this. There are still, Xcache H is still a very recent development. There's still a lot of room to improve. I won't go into that detail, but to say that we're still learning from Xrootd and we're still improving that, but there is a working prototype exists. So this working prototype exists, and we use that with CBMFS. CBMFS is probably another HTTP thing, but it's getting popular. It's a read-only global file system, which mostly used by the LHC experiments to distribute software. So if you look at the plot, the left plot, the circle, on the center, it is the CBMFS Xroot 0, which is the place that your experiments software teams use to publish their software and other things. And they publish there, and this software data will be replicated to those nodes on the circle. They call it Xroot 1, which could be a server, could be a NICAP, well, Bookhaven. The way you publish them as a way to back up this data, as a way to spread the load, and also as a way to shorten the network latency to the specific geographic location. Now, from the Xroot 1, then you start to deliver data to your batch nodes at several sites. And there are two places that Xroot cache is used to spread the load and to do the caching as well. So because of Xroot is used, and Xroot does not prefer large files. CBMFS in most cases we use CBMFS and we avoid distributing large data files. And if we have to deal with large files in a few cases, we chop the large files into small pieces and distribute them. So this is where the Xcache H can play a role here. So the first place we can do is here. We can replace this Xroot cache by an Xcache H. This is actually tested at SLAC and do this as a CVMFS, as a site level cache with CVMFS. We replace it. It's a one-to-one replacement, completely transparent to the rest of the CVMFS and CVMFS distribution network. We did that and it works. There is no reason to believe that we cannot replace it here. I believe we can replace here. And if once we replace here, then we can replace the whole Xroot. We can completely remove Xroot from the CVMFS network. And if we can do that, we also free CVMFS from these restrictions imposed by Xroot. For example, we can use CVMFS to distribute large files more efficiently. We can also build larger clusters with fewer hardware. We always want to have Xcache H working with curl or wget. In this context, curl and wget behave the same, so I'll just use one of them as the example. So there are several ways for curl to work with Xcache H. One is, as I mentioned, you can use a concatenated URL. So you have the Xcache H URL prefix to the final destination. You can also use HTTP proxy or HTTPS proxy. So I listed several combinations here. But everything works except this one last combination, this HTTPS, which you point to a Xcache that use HTTPS protocol, and your destination is also HTTPS. This does not work for Xcache H, but it does work for Xroot. So we want to find out what's going on. So this brings up the question of cache and end-to-end encryption. When everything is HTTPS, people naturally will want to. The reason people use HTTPS is most likely they want end-to-end encryption. So we will compare two different ways of using Xcache. This is the Xcache SLAC that I run, the host name. So the first way to do this is to do a curl command with this concatenated URL. If you do that, the left part of the URL is the Xcache, the right part is the destination. You will see that curl actually sends the HTTP GET command to get from the destination, and everything works. Traffic goes through, you get your data back. And Xcache H encrypt traffic with both ends. But the problem is Xcache can see the data. So this is not really an end-to-end encryption, because Xcache in this case is a man in the middle. You can decide whether you want to trust Xcache, whether this is okay with you, but the fact is that Xcache is a man in the middle. The other way to do this is to use an HTTPS environment variables to point to Xcache, and then you use a curl command. Now, what you will see is that this doesn't work. And the reason is that curl command sends the HTTP connect to the cache, and the cache doesn't recognize it. So this HTTP connect is meant to create an end-to-end encrypted tunnel from the client to the final destination, and the traffic routes through the cache, but it's encrypted. So with such a tunnel, essentially this tunnel bypass the cache. It route the traffic and bypass the cache. So Xroot will honor such a request and will route the traffic through. But because it is encrypted, Xroot will not cache it because there is no value to cache. It's a stream of garbage. Well, in this case, Xcache will just refuse the HTTP connection request because there is no point. We're not doing the traffic routing. Xroot is in this business of doing traffic routing. We're not. Xcache is not. So Xcache will simply refuse to do that. There is nothing to cache. So this brings up the final thoughts about this. It is all about trust, because curl and wget are just two examples. They chose to use get in certain scenarios, and they chose to use connect on other scenarios. This, their choice. Other applications may do it differently. It's up to the application. But this does bring up an issue. We always have this idea of a general purpose shared cache, which is a wonderful idea. But the problem is this end-to-end encryption, in my view, excludes the idea of such a cache. And also the other thing that also is not in favor of this such a cache is the user authentication and authorization, because we can't really practically keep track of who owns the 5 blocks of this particular 5 block in the cache, and what if other people want to access it. So a general purpose cache will have this kind of, a shared cache will have this kind of problem. But this does not say that you cannot build a dedicated private cache. That is still possible, because if the cache is completely under users and the application's control, they control to trust this cache. They can trust this cache as a man in the middle. They can delegate the credential to access the remote data. These are all fine. Or you could choose not to use TLS if the data is public and there is no authentication involved. It's all fine. So this brings us to the summary. Xcache, with all this open plugin architecture, Xroot expanded from a storage system to other type of services. Xcache is obviously one of them, and it actually generates lots of interest. Xcache's function, because of the plugin architecture, is also expandable. And we gave 2 examples. One example integrates Xcache with a central data management system. The other examples emulate the script behavior, but also bring these inherited high-performance characteristics from Xroot. Now, when we develop Xcache Edge, it forces us to think of these things like a general purpose shared cache. We have to think of the relation of the desire of a general purpose shared cache, end-to-end encryption, and access control. So these are the things that are not always quite compatible to each other, but it's not completely excluded. So we have to think of this when we design the application and use cache. So that's all I have. Thank you.
Okay, we'll take some questions.
Hi, Wei. You mentioned some mechanisms of tracking files and metadata. What level of metadata do you keep track of?
So from our perspective, we want to have as little metadata as possible, because once you have a metadata, especially if you put a metadata in a database, there is always a risk of metadata that doesn't match what is on ground, right? So we try as little as possible. I think your specific application question probably regarded to, let's say I have this data in this cache and I have that data in the other cache, and how we understand each other, who has what. I don't think we have a solution right now, but when I look at what Xroot does, they use something called ICP protocols to ping each other. Now, these ICP protocols usually is used by a Xroot cluster that sits next to each other. And in our scenario, if the cache sits next to each other, we probably use the cmsd as a clustering mechanism. So what Alex asked us at that point was actually cache sits in a geographically separated locations. And then the question is, can we use ICP protocols, and whether ICP protocols is efficient over the wide area network or not? But back to the metadata, we try to sort of keep as little metadata as possible, although we try to use real-time query as much as possible, so that we don't have to bring in infrastructures to support too much metadata.
Thanks.
Is it possible to have Xroot on top of cloud storage without a local storage?
Cloud storage, for example.
Like S3.
Yes, you see that. How can I go back? So here is the one. I'm aware of 3 such plugins. One of them is an S3 type of object.
Okay.
I have a quick question that's related to what John was asking. In like the Xroot implementation, does there you could keep track of what cache has the files? Do they do that at this point?
We sort of doing that. I don't think we really spend much time doing that. We have sort of doing that. We also discussed this with Lucille team. Now, obviously, the question is, if a file is a gigabyte and you have 1 kilobyte or 1 megabyte of that piece on your storage, do you tell Lucille or not? Or if you have 900 megabytes, do you tell Lucille or not? Under what scenarios do you tell Lucille? So
yeah.
We have sort of doing that, but I don't think we have started. There are so many other interesting things that people are rushed into. So I think this is one of the areas that initially I was pushing, but when I was focusing on other things, this was left behind.
Wait, this is Rain here. I have a couple of questions. One is, where do the Xrootd and Xcache servers run? Do they run in the user space of a compute node or on the kernel?
Oh, these are all user space applications. They don't go through kernel. The only exceptions is this Xrootd, which is because it's a fuse-based file systems. It actually runs in user space, but it's behind the kernel. That's the only thing. Everything else is just simple in the user space.
Okay.
It is. Is that your question, or is it?
Yeah. And are they all running all the time, or do they run with the application and then die after the application exits?
That depends. The file system you likely will always mount. In most cases, they run all the time to provide service to different users. So it's not a per user service.
Right.
You run it all the time. It's listening to service there, except this very last one, the serverless cache. The serverless cache is similar to all these, except that it doesn't run any daemons. There is nothing really runs. It's just that when you call this Xrootd library, you have to do that through POSIX. The POSIX interface actually catch all these requests and cache it. So it's a completely serverless request, a serverless cache.
Okay. And another question is related to metadata. So how do you search the metadata? Do you need to search the metadata on what data sets are available?
So we don't. It depends on what you mean. Where is that? Yeah, it's here. So in terms of internally what we have, then we use the real-time query. We just basically says that who has this file. And
Okay.
as I said, there are many other mechanisms like database, and we chose not to do that. But the real-time query is what we do. Now, in terms of which data set, if you are talking about experimental data, then that's a functionality of things like Lucille, not our responsibility. But if you are talking about what we have in the cluster, this is how we do it.
Okay. All right. Makes sense. Thank you.
Sure.
Any other questions? Okay, thanks everyone.